Hi there, welcome back to A Slice of Physics. We're going to look at another example of an inelastic collision now, and that's a collision in which the two objects that collide stick together after the interaction. The example we're going to take is two clay balls flying in the air, colliding and sticking, and we want to determine the velocity of the combined ball after the collision. So here's our question for today. It says that a 0.2 kilogram clay ball is falling vertically down at 4 meters per second when it is struck by a 0.3 kilogram clay ball that is moving to the top right with a velocity of 3 meters per second at an angle of 40 degrees above the horizontal. So I've been given the masses of the two clay balls and their initial velocities. It further tells us that the two clay balls stick together after the impact, and it asks us what is the final velocity of the combined ball. So a couple of things here. One is that collisions where objects stick together after impact are called inelastic collision. That's what makes this an inelastic collision example. And inelastic collisions are most easily solved using conservation of momentum. And so here are our solution steps for conservation of momentum problems. Our first step was to identify a system with no net external force acting on it. Only then is momentum conserved. So the two colliding balls are obviously applying forces on each other, but if we take a system where we look at the two balls together, the force they apply on each other are equal in magnitude and opposite in direction because of Newton's third law, so their sum is zero. So in this case, we can say that the system of the two balls has no net external force acting on it. Now it is true that there is the net external force of gravity acting on these two balls. We can ignore that because the internal forces in a collision are typically a lot bigger than the external forces during that very brief period of impact. So that's our first step done, and now we got to sketch the before and after situations. So I'm going to sketch the before situation over here, where the first clay ball, let's call this number 1, has a mass of 0.2 kilograms and an initial velocity, call it v1I, of 4 meters per second downward as shown in the figure. And it's impacted by this other clay ball, call it 2, which has a mass m2 of 0.3 kilograms. And it has an initial velocity that points to the top right like that, call this v2I. And I'm going to reproduce that over here. v2I looks like this, where it's got a magnitude of 3 meters per second at an angle of 40 degrees above the horizontal. The after situation, immediately after the collision, here's ball number 1 and here's ball number 2. They're stuck together as a single piece, and they move in some direction with a final velocity that's common for both. v1f and v2f are the same, so I'm just going to call that vf and not give it the number subscripts. Alright, that's step 2. Step 3 was to establish a coordinate system, and we'll pick our typical x as horizontal and y as vertical. So that's done, and I've listed my known information in the figures, and what I need to figure out is this vf, magnitude and direction. So I've identified that there, and so now we can solve for the unknown quantities. Now since we're using momentum conservation to solve this, we have verified that f external is 0, which tells us that delta p is 0. There is no change in momentum, which means that pi equals pf. Now this is true as general vectors, and because of that it is true as the components as well. So this means that pix for the system equals pfx for the system, and piy for the system equals pfy for the system. So for the total momentum to be unchanged, the x component has to be unchanged and the y component has to be unchanged. So then we will solve this along each axis. So let's take the x-axis. That equation translates to m1 v1i plus m2 v2i x equals m1 v1 fx plus m2 v2 fx. So the system's initial momentum was just the vector sum of the momenta of the individual objects along the x direction, and the same thing for the final state. which is what I have set up here. So now I can plug in my values. M1 is 0.2 kilograms. V1x is simply 0. This ball is falling vertically down, so it's only got a y component of velocity. There is no x component. Plus M2 is 0.3 kilograms times V2ix. So I had V2I over here. Let me label it again at the tip of the vector, and that's made up of two components. I've got V2ix over here and V2iy over there. And when you look at this right angle triangle, the x component is adjacent to the 40 degrees, the y component is opposite the 40 degrees, and the 3 meters per second is the hypotenuse. So V2ix then turns out to be the V2i, which is 3 meters per second, times cosine of 40 degrees, because we're wanting the adjacent side, knowing the angle and the hypotenuse. So that's my left-hand side. And then on the right-hand side, I've got M1, which is 0.2 kilograms. And instead of V1fx, I can just write VFx, because the two balls are sticking together and they have the same velocity. So I don't need to designate it as number 1 or number 2. And then for the next term, I got plus 0.3, again VFX, same final velocity for both balls. So the first term here is 0, and this simplifies to 0.9 times cosine 40 equals 0.5 times VFX. And so dividing both sides by 0.5, I get VFX equals 1.38 meters per second. I'm purposely carrying one extra significant digit because this is an intermediate step. Okay, we're done with the x component, so we know the x component of the final velocity when the two balls stick. So now moving on to the y component, I have m1 v1 iy plus m2 v2 iy equals m1 v1 fy plus m2 v2 fy. Now that we have the equation set up, we can put in the values. So I got 0.2 times v1 iy. It's 4.0 meters per second in the downward direction. That makes it a minus 4.0 plus m2, which is 0.3 times this v2iy over here, and that would be 3 times sine 40, and since it's in the upper direction, it'll be positive. So plus 3.0 sine 40. And on the right hand side, again, I have m1, which is 0.2, vfy. I don't need the 1 and 2 designation. They both have the same velocities, plus 0.3 vfy. And when I simplify this, I will get vfy equals minus 0.8 plus 0.9 times sine 40 degrees divided by 0.5, which gives me minus 0.442 meters per second. So that tells me that this combined object is actually going to be moving downward in the vertical sense. So now I have my VFX and I have my VFY. We got to find the final VF. So let me plot them over here. VFX is 1.38 meters per second. VFY is minus 0.442 meters per second. So the length would be just 0.442 meters per second. The minus is captured in the fact that I pointed down. And to add these, I got to slide the tail of one of these over to the tip of the other. And there's VFY slid over. And my VF is going to be this vector over here. The magnitude would be the length of this. The direction would be this angle theta. So since I know these two sides, legs of the right angle triangle, the hypotenuse is simply the square root of the sum of the squares of the other two sides. So VF would be square root of VFX squared plus VFY squared, which will give me square root of 1.38 squared plus the square of minus 0.442, and that gives me 1.4 meters per second down to 2 significant digits. And then this angle theta, I can say that tangent of theta equals opposite over adjacent, So that would be, I'm only taking the magnitudes, 0.442 divided by 1.38. And when I solve for theta by taking tangent inverse of that fraction, I get 17 degrees. So then I can tell that after these two balls collide, they're going to be moving at 17 degrees below the horizontal to the right with a speed of 1.4 meters per second. In this slice of physics, I demonstrated the solution to a two-dimensional inelastic collision where two clay balls collided and stuck, and we determined the final velocity after the collision. Thanks for watching.